In the next subsection, I want to talk about why this RMQ problem is interesting. And well, by chance, it just happens to be that there's too many abbreviations with 3 letters, or maybe too many long names that need to be abbreviated to be convenient. We should recall Unit 6 for making sense of that motivation. And at that time, Unit 6 was all about suffix trees and suffix arrays. And we talked about the string problem of longest common extensions. So just to refresh memories, we had a single string in the easy version and 2 positions in that string. I probably drew pretty much the same picture back then. We have 2 positions, I and j. And then we ask how many positions starting at these 2 can I move to the right and see the same string. So I want that these 2 green parts are the same, and then the next position they differ. And then the longest common extension was the length of this green part. It's all formally defined on the slide, so and we've touched on that last when we discussed it in Unit 6. The connection at the time where we needed this was to jump around in the suffix tree. We exploited that there's the connection to the lowest common ancestor. So from the longest common extension, you can go to the lowest common ancestor of 2 leaves in the suffix tree. And so these 2 things turned out to be related by taking the string depth of that lowest common ancestor. Remember, memory is coming back. And then at the time, I left you with this unsatisfying black box where I just told you, you have to believe me now. And then we went on. And now it's time to crack that open. So I want to give you, at the end of the session, the full answer to this, but let's work our way there. The important bit from back then was for the longest common extension problem, we needed this lowest common ancestor in the suffix tree. But we also observed at the time already that this is really just the longest common prefix of 2 suffixes. So that was just, by definition, a different name for these things. And then at the time, we didn't have that. But later in Unit 6, we talked about suffix arrays and about the LCP array, the longest common prefix array, which is very, very close to this, except that the longest common prefix array wasn't defined for all pairs of suffixes. Instead, it was defined, if you remember, maybe a bit small. So you listed all the suffixes of a text in alphabetic order. And then for 2 adjacent ones, the LCP array gave you the length of the longest common prefix. But the essential information is still in there. And the relation is this. So the longest common extension of these 2, maybe my infamous picture again. We have positions I and j. Now we ask how much do they coincide at the beginning, so we can draw them on top of each other. That's the suffix starting at I, that's the suffix starting at j. And we ask how many positions can I find there where they're equal before they differ. So that's the longest common prefix query, but between arbitrary suffixes. We don't necessarily have them nicely adjacent. But if you look at this alphabetically sorted list, you notice it's not really that far away. Let me try to pick an example illustrating that. Maybe let's take this suffix and this suffix. So they are not adjacent in order, so we don't have an LCP entry showing us what the longest common prefix is. But we can still trace, so these have one thing in common, these have two things in common, these have three things in common. But we already know these first two, they differ on the second position. So that's like a low watermark. It cannot get better than that. And the same for the others. It's great that they differ on more, but really we need the lowest common thing determines what this and this suffix have in common. So it's exactly a range minimum query on the LCP array. And again, the reason for that is we want the strings to be the same all along. So these two differ on the fourth position, and the first three are the same. That also means this and this, they share the first two characters, but then differ on the third. It's always the smaller of the two that wins. And so if you take two arbitrary positions, it's exactly the range minimum that you have as LCP. Now, the range minimum value, not the position, but you can read that out from the LCP array. And that's what this formula up here says. Let me try to get all of that on the picture. The longest common extension between two suffixes starting at two positions is whatever the LCP array contains at a certain position. And what's the position? It's the range minimum query answer on this array. And now I have to order them because the suffix array, the inverse suffix array, the R array that brings us from the left to the right, it might reverse I and J. If I go from left to right, they might cross. So I have to take the smaller and the bigger of the two. That's why the formula looks a bit messy. But it's not actually more complicated. It's really taking the two suffixes, finding where they are in sorted order. That's what R does. And then taking the range minimum in the LCP array on that position. That's the connection. I know it's a few hops. So maybe you have to pick some arbitrary two strings and do an example. Just follow along what the formula does. The full example is on the slide. So in a way, all the information is there that you need. And maybe that makes it clear. So that's the motivation. That's one motivation for the range minimum query problem. It turns out there are other situations where, again, in disguise, you have the same problem. You have some fixed array, you want to find minima in a certain range. To make the connection quantitative in terms of the performance, we should, well, first of all, we can compute all the ingredients that we have here. So what do we need? We need the inverse suffix array. For that, we probably want first the suffix array and then the inverse suffix array. And we need the LCP array, and then we can start with range minimum queries. We can compute both of these ingredients, or all three ingredients, in linear time. That's things we discussed at length in Unit 6. And so, well, I guess the other thing, any pre-processing okay, I put, maybe we should put, let me fix the slides here. I mean, this is clearer that way. What the next sentence is about to say, you have some solution for the range min query problem. And you can plug that in by the formula on the previous slide to solve the longest common extension problem. How good is the solution you get from that? And so what this says is, suppose you have an RMQ solution with pre-processing time P and query time Q. Then we get a solution for the longest common extension problem that needs the same pre-processing time plus big O of n for computing the arrays. And we inherit the same query time, because we don't actually do anything at the query time other than table lookup, looking at the position in an array. So if you remember what we want, the promise of the black box in Unit 6 was that we can do this in linear pre-processing time and constant query time. Okay, that's what we're trying to do. And especially the second looks quite challenging. And in a way, also the first, that's the time you just need to read the array. If you do any substantial pre-processing, I guess you need to read at least the array you're given. But the claim is that's all you need. It's proportional to the time to read the array once, and then queries are constant time. It doesn't depend how big the array is.